Uh, so today's topics will be, see, we have something like some topics which are like not quite so frequently out there. So some of the topics that we'll be looking at today will be Markovian chains, Markovian decision process, Boltzmann machines, RBM is a restricted Boltzmann machine, Boltzmann networks, deep belief networks, deep Boltzmann machines, transformers, computer vision introduction applications, and some of the case studies. These are all the topics we are going to look at today. Okay, before that, right, I wanted to just understand from here audience, you're all third years and PG. Second year also. Okay. Second year, which branch? Computer science core, and others are third year. Third year. PG students are here. Research scholars, any research scholars? I think in the online audience we are having. Okay. Yeah, so let's get started. This is also getting recorded. Yes. Okay. Visible? Yes. Okay. So yeah, we'll start with Markovian chains. So I wanted to ask before I start, right? Like anyone who I'll stand here so that I'll be visible for the online audience. So is it visible? Yes. Here also, right? Yeah. What are Markovian chains? Anything that you can guess, depending on the presentation here also you can guess. And what part of the entire AML space is it falling into? Anything that I need to correct myself, please let me know in terms of speech or this thing. Right? Yeah. So where is it falling into? Any idea, anyone? Yeah? Yeah, you were the one who was there in the first class also, right? Your good name? Paul. Yeah, what was your answer? Paul?
That it works with the flow of change, or transition between flow of states.
Okay, yeah, thank you so much. Sit down. So Markovian chains is actually coming under association rule mining along with the Prairie algorithm. Like we can identify what are the associations between the data elements. Okay, so let us look at, and whatever topics today we have, right, it will be very useful for, they are like little more complicated kind of AML algorithms, and we will spend some time, good amount of time understanding each of that in terms of how it is working internally and so on. And it will be useful for any research scholars if they wish to do any kind of an use case with any of these applications. So yeah, they are used for identifying the transition, or actually they are used for association rule mining. And one of the best examples that I am giving here is they are used to identify the flow of transition between the states of a categorical variable. For example, you are having, say for example, an Amazon membership plan, right? Or any other plan per se. There is like a gold scheme, silver scheme, and we are also looking at gold and silver schemes are there, and there are also customers who are getting churned. Okay, so we wanted to understand. So this is what we have. Okay, this is given. We are calculating the probabilities. You know how you calculate the probability, right? Probability that, yeah, this is like a front state and to state. We are having like, what is the probability that customers, depending on the statistics itself, they calculate the probability. How do they calculate the probability? How many number of customers have buying the gold plan compared to total number of customers? Maybe out of 180, so it's like 80%, 0.8 and so on. So we have already given this particular matrix. Okay, they are saying like there is an 80% chance that customers who are in gold plan will actually renew their gold plan again. And this means, the second one means that the customers who are in gold plan, there is a 15% chance that they are going to change from gold to silver. Okay. And the third one is like the people in gold, okay, they are going to churn. 5% of them are likely to churn. That means what? They are leaving. They are leaving. Okay. In silver, so I'm telling you how do we read that matrix, right? For the silver part, right? So we are saying that people who have subscribed to the silver plan, 20% of them are likely to convert to gold. 40% of them are likely to say and renew back their subscription for silver. 4% of them are likely to churn. So if you see here, 1% of the people who are churned are likely to return back to gold. 3% of them who have churned are likely to return back to silver. 69% of them are likely to churn again. Okay, so this is all we have. So what they have done is, they have written, they have put this entire matrix as a state transition diagram. If you guys are reading something like finite automata, right? Automata. So you have different states and the transitions between them. If you now look at this particular one, right? If you now look at this particular one, right? So the gold, like I told, right? They're going to stay back 80% of the times. They're going to change from gold to silver 15% of the times. From gold to churn 5% of the times. Okay, in silver, they are going to stay back and renew the same silver plan 40% of the times. They are going to subscribe from silver to gold 20% of the times. They are going to change from silver to, they are churning, they are leaving from the silver plan 40% of the times. Suppose the customers are already churned, right? 30% of them are likely to return to silver, 1% of them are likely to return to gold, and that's it. Okay, so now my question here is, now if you are a managing director, or if you are a person started a business and you have a retail market and you have these plans, right? Or maybe a movies, Netflix kind of a movie streaming platform. Based on this, what decisions will you be making based on this? What are the decisions that you can make based on this? Just simply you can tell. There is no math also. Just think like you understood these things. You are having, now you guys are running a business and you are there as a decision maker. You know all this information. What are you going to do based on this information? Even I also don't know. I'm also thinking in terms of business, right? Yeah, yes, ma'am.
Try to increase the conversion rate between the silver to gold, like improving some.
Silver to gold. Okay. Okay, that is good. Okay. That is one thing he's telling. What is your name? Saravanan. Okay. Yeah, this is, he's saying that let us increase the conversion rate. Like, promote, you mean to say promote the people who are actually, see, you will run some promotion plans at every point of time, right? It won't be there throughout. You can have only for a particular point. You say that there are some offers that we apply. So if you are converting from silver to gold, right? Usually it is available for some X rate, but now you are getting for a discounted rate, 80% off, 50% off. Amazon grants sale and all, right? So that is how you do. That is very good. At least you are thinking in that aspect, right? It's always important, not only you know the technical aspects, you should also know the business aspects. If you have to earn money, correct? You should know the business aspect also. How do you want to cash on that? Whatever is there. That is the reason why ultimately we are using all of this, right? AML solutions or any products that we are going to build, is we want to make money out of it. Correct? Okay, so, yeah, he is correct. The thought process that he has is absolutely right. So some of the things that we can do is a recommendation. Okay, based on what we have currently. Okay, example, insights and recommendation. Okay, so what are the example, insights and recommendation? So the major things they are telling are two things here. Most customers who churn stay churned. but 31% do come back. Of those who return, what did they identify? Of those who are coming back, nearly all of them resubscribe to the silver plan versus gold. So what they are doing is, the business is actually checking at the churn customer base. People who already left, right? If you see here, people who churned, right? There is an arrow mark back to silver. And only 1% of them are going to gold. Which means that they don't want, even if they are coming back, they want to try silver. They don't want to spend so much time on, so much money on gold. So, they don't want customers to churn. That is the main thing. So what they are doing is, they want to give some promotions or some kind of offers for people who have churned to join back to silver plan. That is the main thing there. See, recommendation: launch a targeted marketing to recently churned customers, offering a discount to resubscribe to silver membership plan. So that is how you need to think. Okay. So there is also one more. This is the major part that they are concentrating. What is the one more breakthrough they told? Once customers upgrade to a gold membership, the majority, 80% of them renew each month. So what you identify from this is that 80%, this is a very good amount, right? They need to understand that, okay, people who have subscribed to gold, 80% of them are staying back, they are renewing, which is a very good news for us. So what they are doing is, based on this thing, they are saying that offer a one-time discount for silver customers to upgrade to gold. While you may sacrifice some short-time revenue, it will likely be profitable in the long term. I think like how Sarvana is saying. Absolutely right. You told that only, right? You wanted people more to go from silver to gold, correct? Yes. Same thing they also told there. Okay, so two main insights that the business has taken. Okay. Is that one. Okay. Any doubts here? Okay. Before I go to the next topic, right? So that is about Markov agent. It's not still over. It's also used as part of reinforcement learning. So I wanted to touch upon that, and then we'll go into the next topic. So what is reinforcement learning? In machine learning, you have like supervised learning, unsupervised learning, and reinforcement learning. What is reinforcement learning?
It takes action and
Yes? Yeah, correct. So it's based on this diagram itself you can tell. Yeah, but the major thing that you need to tell guys is like, you have an environment, okay? Action and reward are already there as part of any algorithm, okay? That is also there, but you have an agent who is working on behalf of you, and then there is an environment there. Whenever I say there is an environment, there are certain constraints, okay? Usually, there are so many applications of reinforcement learning, but usually, the way we understand is based on the puzzles and games that we solve, right? There are some rules, which is nothing but the constraints. There is a restricted environment, okay? So in that particular environment only, the agent is doing some actions, okay? So in this reinforcement learning, what you have to remember is that there is a state, okay? There is a state, and there is an action that we are taking on the state, and there is a next state because of what you go, okay? How many of you are studying automata theory, finite automata theory? Oh, ME they have studied, we don't have, okay. Yeah, so in that also you have like the circle, round circles, right? The last diagram that you saw. Okay, this is representing a state, okay. When you are moving from one circle to another circle, all the circles, I mean these nodes are called as the states, okay. And the edges on that are called as the transitions or the actions that they take to move from one state to another state. Okay, so in reinforcement learning also there are certain parameters. There are states, there are some actions that you need to take on the states. Because of the action that you take on the state, you go from one state to the next state. Okay, and there is a constrained environment there. There are some rules. The actions also are limited and there are some rules. The agent will be doing that. If suppose the agent is doing an action in which it is getting it might, for every action that it takes, right, it might be rewarded or it might be penalized. if it is getting rewarded, right, it will try to repeat the same action going forward. If it is getting penalized, right, it will try to adjust itself and correct its course and go back to what it is supposed to do. So there is a source state and there is a required target state that we need to go. So these are all the things that are there in reinforcement learning. Okay, so one example of reinforcement learning is like how you are using to train a dog. Training a dog in the sense like for all the things, like you throw a ball, you bring it back, okay, you teach it to play and so on, right? What are all the things that or actions that you are taking to train a dog? Just one example is coming under reinforcement learning. Because you have a constrained environment, the dog is supposed to, see, suppose the dog is, you throw a ball, it's picking it up and back, coming back, right? You give it a biscuit. Suppose it's not picking it up, picking it back and coming back, right? You'll scold it. Correct? You will try to beat it and say, no, go pick it, pick and come back. Okay, so the dog will keep understanding that, okay, my owner, whenever I bring back the ball, he's giving me a biscuit. So it thinks that, okay, it's a reward for the dog, right? It's happy. So it knows that what it has to do is getting trained on that. Okay, that is a very good example to understand in a very simple way what is reinforcement learning. So here, now we are training a robot kind of a dog. That is the only difference. Now you tell me, I have one question for you guys, like, okay, there are also like available toys where, right, they are pre-programmed. In the sense that you have a program inside, you have a toy, like an embedded system, and then you have a program which is already installed in that, saying that, okay, so as soon as we switch on the dog, it will boot the thing, and there is like a predefined set of programs that runs and it keeps moving. Move your front leg, back leg, like front leg, back leg, and then front leg, back leg, and so on, keep moving. So all of the different actions are already performed. Okay. Now in reinforcement learning, how is it different from that kind of an embedded system?
What to do and what not to do.
How does it, you're right, understand. We will make it understand actually. So how is it different? Like, you're right, but little more. How is an embedded system different from a reinforcement learning in which we are training a dog, a robotic dog, to perform like some operations like sitting, maybe 3 operations are there: sitting, standing, walking. That's it. Robotic dog. So, yeah, any guesses?
Like when the owner of the toy or the dog, electronic dog is like busy, it's like want to sit or take a rest, or when he is like free or when he is like not doing anything, it can ask the owner to like walk, take a walk with me.
Yeah, the concept is correct. Only thing I wanted to make you realize is that, see, there will not be reinforcement learning, right? I will not have any program written inside. Okay. I will not have any embedded program written inside the chip or something like that. You are not putting in reinforcement learning. What you will be doing is you will be building a model in reinforcement learning. You will be building a model in which, right? So you will tell only certain things like, okay, this is your starting state. You are here. You need to go there. Say for example, you will say you are here. You need to go there, and you can take these actions. You can move your. You have only these actions to perform. Go front. Go back, go left, go right, but you are supposed to go from here to there. And you will also tell that if you keep going towards your target, every step you are going towards your target, you will be rewarded. Every step or action that you take which is not going towards your target, you will be penalized. These are the only things that we give as input to that model. We don't have the entire program hard-coded. That is the main difference I wanted to bring here. Okay, so these things only you tell. It will make mistakes actually. We'll tell, okay, you can sit, you can stand. And these are the things that you can do. So it will keep doing. It maybe sometimes it will fall down. Okay. But then it will be penalized. Then it understands, okay, I fell down. This is not what I am supposed to do. Okay. And then it comes back. It moves one step forward. It got a reward. It's thinking, oh, okay, I am on the way to target. Moves one step again forward. On the way to target. It sat down, penalized. Then you understand, oh, I am not supposed to sit. Again. moving. So this is how it learns. And we are building a model, but we don't have a pre-trained program there. Okay, the model will actually make it learn. Okay, there are certain, it will be trained. One trained model will be kept in that particular machine, and these are the things you will have in reinforcement learning. You will have an environment, source state, target state. So please try to understand, because in an interview perspective or in terms of reproducing what you understand, right? So that is where the major difference lies. Okay. Now, for the reinforcement learning, the most important thing is we'll look at another example. Okay, so I want to spend some time on this slide. Have you ever heard of Bellman equation? Yeah, I think the ME students are able to understand. Okay, so this is the fundamental, I mean, being core computer science students, or if you are a research scholar also, we are supposed to understand the math behind the working of any algorithm. Then we will be able to interpret the results better. So the Bellman equation is given as this one. Okay, I'll tell you each of these terms, but let me take some time to look at this puzzle, right? This is also a puzzle. Okay, I'll tell you what these numbers are. These are nothing but the values. Okay, these are all the values. Can I have little silence from somewhere? I think the third bench or something. Please, can I have silence? Thank you so much. Okay, so assume that you have a agent starting here in this particular puzzle. Okay, and then he is supposed to reach this target. So this is again an example of a game in a reinforcement learning. Whenever any of the online things, right? Whenever you think of reinforcement learning, there are many applications, but usually they try to highlight on certain of these gaming applications only. Okay, so the agent is here. This is the target state where it is supposed to reach, where you have a green color flag. If you go to fire, right, then you will be penalized. And assume that this is a wall here. You can't go there. It's a wall. The agent is capable of doing only certain actions. He can go up, he can go right, he can go left, and he can go bottom. He can't go diagonally. Okay, only 4 actions he can do: up, left, right, down. Okay, now he's here. Okay, and now we are building a reinforcement learning so that he will be able to reach from this particular state to that state. So in this entire process, he may be rewarded. If he is going near target, he may be penalized. Same concept. Now I tell you what is the equation here. Bellman Ford, Richard Bellman, right? He has given a mathematical equation in which we can calculate the value of every cell there. Okay, so here I will explain each of these terms here. R is the reward state. Sorry, R is the overall reward that you are getting. S is a state. A is the action that the agent is taking. This is nothing but a discount, gamma. The gamma is a discount. S dash is the next state. If the current state is S, it is moving from S to S dash. Ultimately, what we are calculating is V of S, which means the value when he is in that particular state. Okay, here in Bellman equation, right, the main concept is that two things are there. One is that we are assuming that the value that we are calculating is not depending on any of the prior information. We are assuming that from the current state, we are calculating that information. We are not taking into account any previous information. Okay. So now, okay, so how do we calculate these values from this formula? Okay, given that we are taking gamma equal to 0.9. Okay, so the way we have to calculate is always we should come like a bottom-up approach. Like if you have to go from a source, is it okay? Okay. If you want to go from, so you will have to always use a bottom-up approach, which means that from the target state you start calculating this value, because you assume that the agent is here and it has to the moment he goes to right, if he takes an action of going to right, he will be getting a reward. Okay, so here max, what is max indicating is that when the agent is here, what are all the options he is having? He can go left, he can go right, he can go bottom. Correct? 3 actions are there. But you will be picking only the maximum value, whichever is giving you a maximum reward value, right? That only you are picking. That is what is called as a max. Okay, here I know that the maximum benefit is like if I am reaching the target state. So the reward here is 1. Assume that the reward is 1. Okay. So what we are doing here? So this is point 1. And how did you get a 1 here? Correct, very good. In that, right? So the next state is actually, what is the next state here? Yeah, so here this is a penalty. The penalty is not there. If he is reaching the target, right, the penalty is actually 0. Okay, so he is getting a reward of 1. Only when he reaches the target, he will get a reward of 1. If he is reaching this one, right, he will not get, he will be getting -1. So this is 1. So this part is 1. The reward that he is getting is 1. When he is getting the reward 1, when he is in this state, yes, he is in that state, and the action he is taking is right. Okay, so this is 1, this is actually 0. There is no penalty. Therefore, the value, the entire value is between 1. Okay, so this one you understood how we got 1. Now we need to go back, and then we are here. Okay, so here the value is 1. The value that we are getting is 1. Gamma is 0.9. 0.9 into 1. The reward is 0. So 0.9. Understood? At any other point, the rewards are all zeros. Only at this point, the reward is 1. Okay, so here whenever you are calculating, right, you will have to put 1 into 0.9. That 1 into the penalty is 0.9, or the discount is 0.9. So 0.9 into 1. This is 0, the reward is 0. Any state, the reward is 0. So this is 0, 1 into 0.9, 0.9. Okay, again, when you go here, right, the value is 0.9. Okay, the value that you are getting is 0.9. So 0.9 into 0.9. 0.9 into 9, 81. Okay, reward is again 0. Reward is 0. I am only seeing gamma into V of S dash. S dash is what? The value that you are getting to the next state. So this is the next state. Correct? If you are here, this is the next state. So 0.9. 0.9 is your value here. So 0.9 into 0.9 is 0.81. Okay, so suppose you are here. Again, the reward is actually 0. Okay, and it's like 0.81. 0.81 into 0.9. 0.81 into 0.9, which is nothing but 0.73. So suppose you are here. Okay, so the next state is like 0.73. Here is 0.73. 0.73 into 0.9, which is 0.66. Hope you are able to understand. This is very, very important. Yes, ma'am? Did you understand? Okay, this is very, very important. So I have got all of these values, right? Now we will see how we got these values. Here also same thing. See, he will understand that he can go this way to reach the target, or the agent can also go this way to reach the target. Correct? If it is this way, right? Again we need to backtrack. Okay, so from here it is 0.1. Same way how we got 0.9 here. 0.9. Okay, because here the value is 1. The value that you are going when you go to the next state is 1, because we have to decide this one. So 1 into 0.9, 0.9. So if you are here, right, the value that you will be getting if you go to the next state is 0.9, 0.9 into 0.9, 0.81. When you are here, the value that you will get when you go into the next state is 0.81. So 0.81 into 0.73. Sorry, 0.81 into 0.9 is 0.73. So here, the value that you get when you go into next state is 0.73. So 0.73 into 0.9, which is 0.66. That's how you got all of these values. This is very, very, very important in terms of understanding how a reinforcement learning works and how do you calculate the values. Okay, so here There are two methods in Markovian decision process. One is called as a deterministic search, the other is called as a non-deterministic search. Okay, in deterministic search, what happens is that you have only one action that can be performed. The probability of performing that action is actually 100%. And there is no other probability. That is called deterministic. Okay, the agent is here and the probability that he will go up is 100%. This is called as deterministic search. Deterministic search means the probability that the agent will take that action is 100%. Okay, in a non-deterministic search, the probability that he will take that action is not 100%. It is split. There is some probability. He may go left, he may go right, or he may go up from this particular state. Just for example, they have given, if it is 10% probability that he goes left, there is 80% probability that he goes up, there is 10% probability that he goes right. So that is what is given here. There are two cases, but Markovian decision processes are applicable only if you have a non-deterministic search, not a deterministic search. That you have to keep in your mind. Any questions still here? Yeah. Okay, so the analytical formula for the Markovian decision process is whenever there is a non-deterministic search, right? This particular thing is getting expanded. Okay, when it is a deterministic, it can be applied in both cases. Okay, when it is in deterministic, then you have only B S dash, or you can say S prime also. That is the next state. S is your current state. A is the set of actions. Sorry to actually repeat the points again and again, because these concepts are little complicated and you need to understand the math for understanding the concepts. So I am stressing it again and again and making sure that some of that goes to your mind. So S is the current state. S is the state, A is the action, R of S comma A is the reward that you are taking because of moving from state S with an action A, and this is nothing but the discount, gamma is the discount. B of S prime is nothing but the value that you are getting when you are going to the next state S prime. Okay, overall value you are calculating, you are moving, because of moving from S to S prime, what is the overall value that you are getting it here. This is the same formula whenever you are using a deterministic search, but in case of non-deterministic search, where you are not sure, there can be a probability that you can go left, right or something, top, right, then you will have that probabilities in between, where 0.8 into the next state, or 0.1 into the next state, or 0.1 into that next state. So that is how your formula will be altered. Okay, so what it becomes is like, in general, the formula now becomes like same thing, but you have a sigma for all the different states that you can go. Sum of all of that, right? The probabilities of sum of S comma A comma S dash into the probability into 0.8 into. So probability of moving from S to S dash by taking that A, that probability into V of S dash. So all of these summations and the same formula. Why are you having max? Because you will actually take the maximum value among all of this. Okay. Okay. So now this is where your Markovian decision processes are. This is the formula and this is all the entire thing of your. Whenever you are having a reinforcement learning, the main concept in reinforcement learning is the Bellman algorithm. Sorry, Bellman formula or Bellman algorithm. So, what are the applications? Okay, if anyone is trying to pursue their research, right? If you are research scholars, what are all the applications of Markovian chains? Population harvesting, agriculture, water resources, okay, finance and investment. We can know, like, given my current state, when I can invest, given which day I can invest, how much amount should I invest? It is like how you have to build your problem is that you have to take the current state, what action you have to take, what are the constraints that are there, what is the next state that you are going into, and what is the value that you are getting as because of taking all of this. And you also have to determine whether it will be a deterministic search or a non-deterministic search. So these are all some of the applications of, see, so many applications are there. Okay, and it is still not explored. Any of you want to put a paper or do some research, right? You can take the concept of this Melvin algorithm and Markovian decision process. So you have location, design of experiments, patient admissions, sports, credits, epidemics, overbooking, motor insurance claims, search, sales promotions, queues, finance and investment, and so on. Okay, so we are going into the next one. Okay, before I proceed to the next topic, right? On the day one, actually I have covered feed-forward neural network, and we have also seen convolution neural network. One thing that we have not seen is a recurrent neural network. Okay, I'm going into deep belief networks and Boltzmann belief networks and so on. But to understand that concept, right, we need to understand some knowledge about recurrent neural networks. Okay, so anyone here who can tell me what is a recurrent neural network depending on this one, right? And what is the difference between a feed-forward neural network to a recurrent neural network? Yeah, self-loop, yeah. From the diagram, he is telling that there is a self-loop, which is correct. Okay, so which means what? Self-loop, which means what?
Previous plus current information.
Yeah, correct. So actually, in a feed-forward neural network, the weights will be propagating. The error will be propagating only in one direction. That is in the forward direction, from the input to the hidden layer to the output. But if you take a recurrent neural network, it will be the weights, in the hidden layer, you will be doing a feedback back. You will take the output and feed it back to the same thing again. Which means that you are storing a current state, you are having a memory. You are also determining the current state also. You have a memory, you are feeding back your outputs back to the input. So because of this orientation, what will happen is that it can be used in time series analysis. Okay, recurrent neural networks can be used in time series analysis because of this particular feedback loop, memory and all, right? And we will look at at a very high level, we will look at what are the different types of recurrent neural networks, what is the basic thing in that, okay? So I told you that because of the looping, right, it can have an information about what is its previous state, it will store some memory, and it is used in time series algorithms. So time series means what? You are having x of t, the input is x of t is the value at time t, x of t minus 1 is the value at t minus 1, x of t minus 2 is the value at t minus 2. This is your x input. You are also having the value of x of t plus 1 and x of t plus 2. Okay, so here H represents the hidden state and Y are all the output parameters. Okay, so here what is happening, if you look at here, right, see here in the hidden state, there is always a feedback back to the same hidden state. That is the main concept of a recurrent neural network. You have a feedback where you are storing the value of the output back there. So you have information about the current state. Okay, that same thing is getting passed on to the other states. So because of this orientation, this is one particular way how you are representing a recurrent neural network. Because of this, it is used in very good for time series forecasting of the. What is the problem with recurrent neural network? It is used in time series forecasting. It has a memory element. There is a feedback back. So the direction is not always forward. What are the disadvantages of recurrent neural network? Anyone? Infinite? No. You should remember one jargon. It's called as vanishing gradient and exploding gradient. Okay, in recurrent neural network, what happens is that when you are keeping these feedback loops, right, the weights that are associated, right, the weights will, there is something called as exploding gradient and diminishing gradient. Both of these two things can happen. That means that the weight values can increase drastically over a period of time, or the weight values can decrease drastically over a period of time. Because of that, that is a huge disadvantage in the recurrent neural network. Okay, so there are some other variations of recurrent neural network, like gated recurrent, GRU, LSTM. So they are coming into picture. Okay, so you already know, I think in the last 3 classes, right? You already must have known artificial neural network, right? Artificial neural network is the basis to get started, right? You have a perceptron, and then the artificial neural networks are used for regression and classification kind of algorithms. Okay, what is the difference between regression and classification? What is the difference between regression and classification? This one I will expect you to answer, it's very basic only. Correct, correct. Regression? That is recursion. Don't get confused with recursion and regression. Okay. What you told is recursion, calling a function, same function again is a recursion. Man, I think people are little dull, okay. What is recursion, man? What is the difference between classification and regression? Because I am taking a concept on what do you call Markovian chains, Boltzmann machines and so on. You have to have a basics of what is the difference between regression and classification. I think any students can answer, but I am expecting someone from second years. Regression is not recursion. Please be careful. Okay. Yeah, regression means, and in any machine learning, I am getting some noise actually. That's right, huh? Yeah, so, yeah, regression means that the output variable is continuous. You are having examples like prediction of house prices, prediction of car prices. In the machine learning, whatever prediction you are doing, if the output variable is continuous variable, it is called coming under regression. If the output variable is a categorical variable, if the output class variable that you are trying to read is a categorical variable like male, female, number of states, or high, medium, low, and so on, it is coming under classification. Please don't forget the basics. Okay. And okay, so artificial neural networks is used for that purpose. Then you are having the advanced one, which is convolution neural networks. Okay, convolution neural networks usually they can be used for even text-based also, but usually they are applied for image processing and computer vision. Then you are having the recurrent neural networks that I told you just now. They are used for time series analysis. What is an example of a time series analysis? Weather forecasting, humidity. Okay, anything that changes with time, every second it changes. What is the temperature now? What is the humidity now? What is the pressure now? Anything that changes with stock market analysis. All of these are coming under time series analysis problems. Time series analysis problems are completely different from the usual set of regression and classification algorithms. They have to follow separately some procedures. Time series means what? Something that varies with time. Okay. So these recurrent neural networks are best suited for time series. Now I am coming to something else. Self-organizing maps. So all of these first 3, right, which are in blue color, they are all supervised algorithms. All of them are supervised algorithms. Now, self-organizing maps, deep Boltzmann machines, autoencoders, these are coming under unsupervised algorithms. Okay. What is supervised algorithm and what is unsupervised algorithm? Supervised algorithm means you are having training and testing under the supervision of that class label. You know the class label, and there is a training and testing that happens. In unsupervised algorithms, there is no class label. Okay, so there is no training and testing. We are only grouping. There is only grouping and clustering. So these are all coming under unsupervised algorithms. Self-organizing maps. It is also used for feature detection, SOMs. Okay, I am not covering SOMs today, but there is an next step. Then you have deep Boltzmann machines, the topic that we are discussing now. It is used for recommendation systems. Whatever topic now I told, deep Boltzmann machines is used for recommendation systems. First of all, we need to understand what are these. I told you Boltzmann. What is a Boltzmann machine? I mean, I told you Markovian decision process, right? And reinforcement learning and so on. We will look at deep Boltzmann machines now. Autoencoders, they are also used for recommendation systems. So they are all coming under unsupervised. I will ask you questions at the end. I'll see if somebody is able to answer them. I will give some prizes. Okay. So from this diagram, right? The first one that you are seeing here, right? Can you tell me what it is? No, I'll tell you. See, it's a ANN, artificial neural network. This is a CNN. Okay. This is an RNN. This is an SOM. So I have not given the labels. Okay. Once again, I am saying this is an ANN. Why is this an ANN? First one is an ANN. Okay. Why is it an ANN? Because you are having input nodes are there, hidden nodes are there, output node is there. Input nodes are connected to the hidden nodes, and then this is basically the architecture of an ANN, artificial neural network. Then if you see the next one, right, you have an image, and from the image, this is the convolution operation that you are performing. After the convolution operation, convolution is nothing but you are trying to multiply f of x and g of x two functions. You will apply a filter or a kernel, and you are trying to apply that particular kernel, and you are getting that convolution neural network. After the convolution, you are having a pooling layer. Okay, yeah, either max pooling or min pooling. The pooling is nothing but you are taking the maximum among that value or the minimum or average and so on. Then you are getting your flattening layer. This is the flattening layer. The output of this again is given back to your ANN. This entire thing is coming as a CNN. Okay, this entire thing is a CNN. Here, this is a recurrent neural network. Whenever you are having this diagram, right, one input node is there, one hidden layer is there, one output node is there. You are feeding, in the hidden layer, you are feeding it back to the same thing. I told you that whenever there is a self loop in the hidden layer, it is coming under RNN. Whenever there is a self loop in the hidden layer, it is coming under RNN. This is an RNN. In the self-organizing maps, right, though we have not studied, that is used for clustering or unsupervised algorithms. Okay, in that particular sample space, right, it is trying to pick out some projects and we do the clustering. Self-organizing maps will learn that by themselves. Now, these are Boltzmann machines. Any diagram that you are seeing like this is an example of a Boltzmann machine. Now, tell me the difference between what is the pattern that you identify here and what is the pattern that you are identifying here. In the first four diagrams, what pattern you are identifying? Here, what pattern you are identifying? And how are the Boltzmann machines different from the first one?
Each nodes are connected to each other. Each nodes are
Okay, that is one point. Yes, next.
Compares everything with the other.
So we'll go for a 10 minutes break. We'll come back after it.
Students, after the break, come back.
You right? So here you can see that. You can see that in the first four diagrams, right? It's always on the forward direction, but the Boltzmann machine that is there below, right? You are not only having forward; it is connected in all ways. Every two nodes are connected. Okay, so there are also other differences when compared to machines, right? Boltzmann machines can be represented for. See, there are two colors in Boltzmann machine. One is a blue color, the other is a white color. Blue color nodes are called as visible nodes. White color ones are called as hidden layers, hidden nodes. Okay, the difference between the other things is there are so many differences. One of the main differences is that every node is connected to every other node, and also if you see, right, there is no forward connectivity only. The error propagation, the weights are not only propagated in the forward direction, they are also backward and everywhere. It's like a kind of an undirected graphs everywhere. Okay, the other one is that if you see the input nodes, the blue nodes itself are connected to each other. The blue nodes itself are connected to each other. Okay, so in these aspects, the Boltzmann constants are different from the other neural networks. So they are used to model complex features or extract complex features from the given data set. So if you look here, there is a bigger diagram of a Boltzmann machine. All the orange color ones are the hidden nodes. The blue color ones are also called as the visible nodes or the input nodes. Like I told you, the main difference between the other neural networks to the Boltzmann machines is that in the Boltzmann machines, every node is connected to every other node. There is no direction. It's like bidirectional. And also the input nodes are connected to each other. That will never happen in any of the other networks. The input nodes are also connected to each other. Okay. So what is the basic concept behind the Boltzmann network? They are all energy-based models. Okay. They are all basically energy-based models. So the probability of existence, the probability in the ith state is given as e to the power of this E here, right? The small e is called as the energy. Okay. K is called as a constant, T is called as a temperature. E to the power of minus sigma I by kT. Denominator will be sigma j equal to 1 to m e to the power of minus ej by kT. So here if you can see, if you draw a relationship between the probability of occurrence in one particular state I is inversely proportional to the energy. As the energy increases, okay, as the energy increases, the probability decreases. Or if the probability increases, should I start? Okay. If the probability increases, energy decreases. So the probability of existence in one particular state, for one particular state, is inversely proportional to the energy based on this given equation. If you have to understand energy-based models, right, there is an example. Suppose there is a room, just like our room, and you see all of these small dots here. They are all the molecules. Okay, so what is the scenario? What is the probability that the molecules can be freely available compared to the probability that all the molecules are packed in one place? Which is quite likely possible? First scenario or second scenario? First scenario. So the Boltzmann energy model, it says that the lesser the energy, the stable the model is. Okay. The probability is actually the lesser the energy, the more probability is. So here also you can see, when the energy, the molecules are all packed at one place, the energy will be greater. Okay, when the molecules are all packed in one place, the energy is greater. So the probability is lesser. That is what you need to understand from this diagram. If the energy, the molecules are all scattered, then what happens? They are in lower energy state, which means the probability of that is higher. That is what you need to understand based on the energy-based models. These are more complicated mathematical models that are used. Okay, so this is a simplified version of understanding what is a Boltzmann machine and how they are energy-based models. So the formula for any energy-based model in a Boltzmann machine is given as E is nothing but the energy, V is the input state, H is the hidden state. Okay, and A and B are the biases. In any multi-perceptron, right, you will have B as a bias, right? Here A and B, two variables are there which are the biases. B is nothing but the input state, H is the hidden layer. So the energy is a combination of the input and the hidden layers, which is given as minus of sigma I ranging from AI Bi multiplied AI Bi minus sigma of J Bj Hj minus sigma of I and J Bij Wij Hj. Here in the last one you are doing like a product of the input layer, the weight between the input layer and the hidden layer. Wij is the weight between the input I to the J. Okay, this is the main mathematical formula behind the energy-based models. This is how you calculate the energy. Once you have the energy, right, you can find out the probability of occurrence in a particular state. So, whatever we studied till now is called as a Boltzmann machine. But in general, Boltzmann machines are directly not applied in any of the real-time use cases. We will be using a restricted Boltzmann machine. What is the difference between a Boltzmann machine and a restricted Boltzmann machine? If you look in the diagram, you can understand. Yeah, see, in a restricted Boltzmann machine, right? So the input layers are not connected to each other. Okay, there is no connection between the input layers. The visible nodes are all connected to the hidden layers only. Okay, the input nodes, it is something similar. If you actually rotate the diagram 90 degrees, right? It is almost similar to your artificial neural network only, where you have an input layer and a hidden layer, correct? Okay, so these are the ones that are normally used for real-time use cases. These are restricted Boltzmann machines. It's also called as RBM. Main difference between the Boltzmann machines and the restricted Boltzmann machines is that the input nodes are not connected to each other. Okay, if that complexity you are removing, right, then they will become little more simpler versions of the Boltzmann machine, which are easier to model. So, what is an example in a restricted Boltzmann machine, right? In real-time use cases, ma'am, we have been telling about Boltzmann machines, but what is the real-time application? Like I told you already, these are used for association rule mining and recommendation. Mainly Boltzmann machines, any research scholars can apply that as a recommendation. What kind of a recommendation? Say for example, we all can understand movie recommendation. You can assume that all of the input nodes are some form of movies. If there are some form of movies out there, okay, so you can actually recommend for the users in Netflix, right? If I am watching some number of movies, then it will tell me, you watched this movie, you watched the other movie, you can also likely watch the other movie. How is that it is able to tell us? How is that the system is able to tell us? Tell me. Yeah, so it is there in there itself, correct. So, so internally what is it doing? How is it able to tell us like Netflix or any other system, right? If I watch a movie, how is it able to tell that if you watch movie A and movie B, you may also be interested in movie C?
They come in the same class of germs.
Yeah, so first of all, what it has to do internally is that it will have to train itself depending on the movies. And there is one thing given by the user. What is that one thing given by the user? Just based on the movies, it won't. It has to actually build a user profile. Suppose we are all the users, right? We are watching movies. Every user will have a profile towards them, associated with them. I will give the feedback on the movie. Once I watch the movie, I will give the feedback. I will tell it is good or bad. I can give so much feedback, but the minimum feedback that I can give is like, either I liked the movie or I did not like the movie. Based on the movies that I watched and the feedback that I have given, it will build a customer profiling or a user profiling. Okay, so what it will do is, see here, okay, you can see on the topmost corner, right? So this is how you will have an Excel file. Say for example, you have 11 users, user 1 to user 11, and there are 6 movies there. How we have to read this Excel file is that the user 1 has watched movie 1, movie 2, movie 4, movie 5, movie 6. If there is no entry here means that he has not watched movie 3. Okay, either it's a 1 or a 0. 1 means that he watched the movie and he liked it. 0 means that he watched the movie but he did not like it. Like that you can take. So like that you are having user 2, 3, 4 and so on. Now, okay, this is how it will have the data, Excel files data. This is nothing but the data set you are having. Now we can apply. You can ask me where I can use the Boltzmann machines. This is the example. Restricted Boltzmann machines can be used for movie recommendation, where we are telling like, given this particular data, where users are watching some movies. Okay, now tell me, based on this, when a new movie is coming, can I recommend it to a user or not? Okay, when there is a new movie, should I recommend to a user or not? Okay, so now based on this data, right, can you tell me anything that you can find out? Any insights that you can find out based on this data? Like you should tell me some insights in a way that you should say, okay, if the user is watching movie 1 and 3, he is also watching 4, ma'am. If a user is actually liking 1 and 3, he is liking 5, something like that. Can you identify anything from here? Can you identify any pattern from here? What is happening?
User 1 and 4 follow some similarities, ma'am. Like user 1 for, liked the movie 1 and disliked the movie 2, and also like the movie 4. Say as like that same.
Oh, so 1 and 4. So you are telling there are two kinds of things that we can do here. What you said is absolutely right. Very good, super. Okay, this is just observation only. Okay, so there are two kinds of things that we can do based on this data set here. We can do like user to user comparison. We can do. Okay, because see if you we can do like a we can compare users like how we did, right? I can compare row wise or I can compare column wise also. If I am comparing row wise, right, I will say that user 1 and user 4 is telling they have similar profiling because they both liked one movie, they did not like another movie. So then based on that, what I can say, if user 1 is liking the other movie, right, it is likely that this guy also is liking the same movie. So user 1 is not liking one movie, right, that is likely that user 4 also is not liking that movie. So whatever movies user 1 is actually watching and liking, they can all be recommended to user 4. Very good, super. These are the insights that I wanted to ask you guys. Okay. There can be another insight based on the column as well. Based on the column also. Anything that you can find? Even I am also not sure. I am just trying to see. One more thing is, irrespective of the user, you are thinking in terms of user, right? If user 1 and user 2 and so on. But there is also, look at the column wise also. What I am thinking is like, if they are watching movie 4, 3 and 4, they are also watching, I mean they are liking 6. 1 and 4 if they are liking 6 also. 1 and 4 if they are liking 6. 1 and 4 if they are liking 6. There are many patterns like that. 1 and 4 if they are liking 6. So I will derive one pattern. It may not happen all the case, but I will derive a pattern saying that irrespective of the user, across multiple users, if they are watching movie 3 and movie 4, they are also likely to watch movie 6. Okay, that is what I understood. So suppose if a new user is coming, he is watching movie 3 and 4, I will put a pattern like that in my thing, and then I will say, okay, if he is watching movie 3 and 4, I will surely ask him to watch movie 6. Okay. So guys, actually this machine learning or data science is all about your intuition and common sense, okay? Though there is mathematics behind that, right? Now these days you need to understand that, but you need to concentrate more on putting little common sense, focus and thought process, okay? So you can't expect the system to do everything for you, okay? You are given a data set, right? Even before you proceed with your code, right? You might be thinking hands-on, everywhere they are asking hands-on. But before hands-on also, you should know how you should think, right? That is why some of these sessions will be useful. Understand? And recommendation systems are quite a lot used in our industry. Okay, user recommendation and item recommendation. There are three types of recommendations. User, item. Okay, now what I am telling column wise is an item. Item in the sense movie. Movie 1 and movie 3 and movie 4, if they are watching, they can watch movie 6. Like how he told you. User 1 and user 4, user recommendation. Based on user and user. Based on user and item also you can give recommendation. User and movie. Okay, so please try to concentrate in terms of putting some common sense. Okay. Okay, before I tell you, like, see, what I am saying is common sense is very important. We might do the entire code. You can get the code from the internet, you will run. But the problem you will not understand is that where you are going wrong. Okay, what is it that you need to do? You will understand only if you understand the data set. Apply common sense. Okay, that is where you need to focus. So people are not becoming great because they are doing different things. People are becoming great and successful because they are doing things differently than others, not different things. Okay, Elon Musk or whatever, right? He is successful with so many businesses, not because he did different things. He did things differently than others. He took so much of risk. He also doesn't know anything about space when he started, but he explored, he took that risk. He used common sense also. He used a business value. So what I'm saying is at the end of the day, it's not about a tool, technology, programming language. mathematical concept. It's about how you perceive, okay, how you take things. What is your common sense and how much ready are you to take that risk, okay? Anyway, why here I'm saying we are spending some more time because I want you to, these concepts are not that easy to understand because there is a lot of maths involved and also there is a lot of application also. So I want you to pause some time, take a moment to observe and then give your insights on it. Yeah, so like I told, right, movie 3, 4 and 5, that is one insight that we can derive from the data. If people are watching movie 3 and 4, right, they are also likely to watch movie 6. Okay, now I have, there are some movies here. Okay, actually the question was like, I did a copy paste from that, but the question here was like, given these particular movies and given that, one more thing, these features that are there, right, is it identifying by itself or are we asking it to identify? In a recommendation system, in the Boltzmann recommendation system, are the features automatically extracted or are we telling what are the features to be considered? Yeah? In the recommendation system using Boltzmann machines, when it is trying to build a model, are the features automatically extracted or are we telling what to concentrate on? Usually, based on the movies, it will be given only the data set. It is automatically extracted, okay? It will itself form, like, okay, based on this user and these movies and the ratings that they have given, right? It will automatically extract the features. So it is having some of the features as what? Like you saw previously, right? There was a genre feature. Genre, it's not always about genre also, it's about the actor also sometimes. People like the movie because of the actor. It's not only because of the actor, sometimes it can be because of an award. Oscar winning film that many people are watching. So it can be because of genre, it can be because of actor, it can be because of the award that it's getting, right? So here, the genre is drama. The genre is action. The name of the actor is DiCaprio. Okay, and it's an Oscar winning. And Tarantino, I think he's also an actor, right? Director. Oh, okay. So he's a director. And I don't know how many of you have watched this. I think I watched only The Departed. Have you guys, anyone who watched all these movies? English one? Matrix also I think I watched. Fight Club, I don't remember. Titanic I watched, sorry. Titanic I watched. Anyone who watched all of these movies? You watched them? Oh, super. Okay. At least this question, I'm getting some answer. Okay. So, so you need to tell me now, like, the Matrix is what? Is it a drama? Where is it falling under? Action. Matrix is action. Okay. Fight Club? Action. Forrest Gump? Drama. Okay. Pulp Fiction? Action. Okay. Titanic? Drama. And also actor also, right? I think Titanic, DiCaprio. Okay. Why I am saying is this. See, it will have information on the movie also. Now, which nodes, the model how it will do is, which nodes to activate. The problem here is that whatever is in blue color, right, that is a training data. That means that we know when the user is coming newly, whether the movie has been liked or not liked by a user, 0 and when there are these white things, right, I don't know. When a new person is coming and they are watching whether they will like the movie or not, I need to tell. I can tell only based on all of these hidden nodes. The hidden nodes are nothing but it is automatically identifying the features based on what they liked and what they did not like. Okay. So here, Fight Club, they are saying that depending on this data, okay, so I think Titanic is drama, Departed is what? Drama or action? Not sure. Okay, based on all of this, right, all of the nodes are active nodes. That means it is taking input from all the active nodes. Now you guys have to tell me, think logically and tell me, it is telling that based on this, for one particular user, if he is having 0101 score, Okay, and these are the two movies. It is actually recommending The Departed. It is telling that they will like The Departed. They will not like the Fight Club. You guys, I think you have to answer why. If the user, what does this indicate? I am giving you one instance of the state. Okay, what this indicates is that whenever a user is there and he is liking this Forrest Gump, Titanic, The Departed. Okay, sorry, this is not there because this is a blue one. Only 4 are there. Okay, he is liking Forrest Gump and Titanic, and he is not liking The Matrix and Pulp Fiction. That means he is not liking action movies, correct? Yeah. So in that case, will he like Fight Club? No, because it's action movie. As simple as that. Will he like The Departed? It's not action movie, it's drama. He will like. So what? Understood? As simple as that. Okay, whatever we are trying to apply, same thing it is also applied. Okay, thank you so much for listening patiently. Okay, now, okay, so just like in feed-forward neural network, artificial neural network, and so what is the algorithm that is used in all of that? The main algorithm, backpropagation algorithm is there. Okay, what is backpropagation algorithm? You are actually propagating the output back through the network so that you can adjust the weight and minimize the error. That is the idea of backpropagation algorithm. Here, in Boltzmann machines, there is no backpropagation. The algorithm is called as contrastive divergence. The algorithm is called as contrastive divergence. Okay, it is also similar to your backpropagation algorithm. The main concept is that you have to reduce the error, but the way it is done is in a different fashion. Okay, the blue nodes are nothing but your input nodes, and red ones are the hidden nodes. So what it will do is it will have a sequence of steps in which the input nodes, okay, will actually help them to come with the, like, how you have to understand is that you are having the recommendations of the movie, right? So based on the recommendations of the movie, it will form the genre. Again, suppose you are getting new test data, right? Sorry, train data. Based on that, again it will update the genre. Initially, it will have like everything is like genre. But later, because of the input, it has identified that genre only is not the thing. The actor and the Oscar award also is important. It will again update. Again, based on another input, it will update the features. Like that, will go on. Okay. Yeah, thank you. So that is what is called as contrastive divergence. It is similar to this particular graph where you are actually calculating the slope of that. Okay, this is also similar to your backpropagation algorithm at any point of time, right? If you check that, right? B is nothing but the input, H is nothing but the hidden. The difference of that is nothing but the gradient. We should always try to reach a state where the energy is minimum. Okay. Or here we are telling, see, only difference is that in the normal networks and all, we tell it is error, but here we tell that it is energy. The energy should be as minimum as possible. Okay, we have to bring it in such a way that the energy is as minimum as possible. Here how we are applying is nothing but delta of log of the probability of the input by the change in the weights, Wij, when you are moving from a state I to a state J. I and J are the states. Bi is the input state. Hj is a hidden state. The difference between Bij to Bij infinity, that means you are moving from 0, 0 to infinity. So the algorithm that is used in Boltzmann constant is called as the contrastive divergence. Just like you have backpropagation algorithm in ANN and feed forward. Now from a so we have seen Boltzmann machines. Okay, Boltzmann network. Now we are going into deep belief networks. What are the deep belief networks? Is it also looking like a Boltzmann only? Yeah, it is also looking like a Boltzmann. The thing is that it's a stacked Boltzmann. Okay, in a Boltzmann network you will have only one input and one hidden layer. But in a stacked Boltzmann you will have multiple, like this. There is one Boltzmann, another one, stacked on top of other. And the main important feature in the one of the topic that they have given is a deep belief network. Okay, in the deep belief network, what happens is that you have a stacked Boltzmann machines, one on top of the other. Okay, And then you can also see that the inputs are not connected to each other just like in any other RBN, restricted Boltzmann machine, and that you are having a direction, though they are not, everything here is like undirectional, but except for the last layer, in the intermediate layers, the direction is towards the input layer. That is the propagation, the back propagation of the weights or the error is towards the input layer. That is the main concept in the deep belief networks. So in deep belief networks, there are two training algorithms that are widely used. Greedy layer-wise training algorithm and a wake up and sleep algorithm. Okay, so there is a stacking on the RBMs also. The restricted Boltzmann machines are stacked vertically one on top of the other. So you can make a note of the training algorithms that are used. The deep belief networks are more complicated mathematically compared to any other machine learning algorithms. So what happens here in the greedy layer-wise algorithm, right? In a greedy layer-wise algorithm, layer by layer it will be calculating the weights in a greedy manner. I don't know how many of you have studied DAA, Design and Analysis of Algorithms. It is there, right? Second semester, now it is there? Happening, right? Okay. In Design and Analysis of Algorithms, you are having all the algorithm design strategies. One of that is greedy. So two main things are very important for the topics today. One is a greedy algorithm, the other is a dynamic programming. In greedy, what is happening is you will always get the output optimal. Okay, optimal solution you will get, but you will not, the optimal solution may not be the, you may have n number of feasible solutions, one of that can be optimal, so it will end up in a local optimum. It need not, the optimal solution need not be the global optimum in a greedy algorithm. That is the main concept there. Okay, so greedy algorithm is like at that particular point of time, whatever is the available best thing, it will go ahead. For example, a traveling salesman problem, when I am moving from point A to point C, okay, and then you have some number of costs that are associated when you are moving, right? At every point of time, what I will do is, okay, from here if I have to go to the next node, which is the least possible cost? 2, 8, 9 are there. I will go to 2. Okay, from that particular node, I am not bothered whether from that 2 again if I am getting 16, 17, right? I am not bothered. Then I am having 16, 17, 32. In that I am going to 16. Whichever is least in the available set of networks, there I try to go. But at the end of all of this process, right, whatever solution you are getting may not be optimal. Okay, so that is a thing for greedy algorithm. But in case of dynamic programming, what happens? In case of dynamic programming, what you will do is, initially before even taking a decision at the source node, what you will do is, you will have a matrix where you will try to calculate all possible things that can happen, all permutations and combinations of how you can take the path to reach the checkpoint. Okay, suppose you are going from a node A to C, right? You will have a matrix where you will put from what are all the ways in which I can reach from A to C. Okay, among all of those, whatever finally you are getting as the minimum, right? It can be one or more also. There might be n number of feasible solutions, but there will be one optimal solution, one or more optimal solutions, and the optimal solution will be a global optimum also in case of dynamic programming. So which is better, greedy or dynamic? Yeah. So what is the, I mean, better in the sense you should ask me the question next, ma'am, in what aspect you are asking. Okay, if you are thinking in terms of, because you always have to, which is better means you should always ask me in terms of time complexity and space complexity. Okay, actually dynamic programming is more complicated the way when you are implementing. Greedy is very easy. So in terms of time, greedy takes less time. Dynamic programming will take more time. Okay, in terms of space also, dynamic programming will occupy more space. So both time and space, but in terms of efficiency, dynamic is better. But in terms of greedy, right, it will be very less amount of time you will be doing, and very less space also it occupies, not much, because every point you have only the next set of decisions that you need to take. You will not be having a bigger picture. But at the end, are you reaching a global optimum? No, with greedy you are not reaching. So if the efficiency is a matter for you, go with dynamic programming. No, if time and space complexity also matter, go with greedy algorithm. Okay, why I am saying is they are using a greedy layered approach in order to find out the weights at each and every layer. Okay, now all the layers, layer 1, layer 2, layer 3, they are using greedy programming in order to arrive at the optimal weights. How? A-star algorithm. Heuristic. So what is the difference with what is heuristic?
Like, if the step, if from the step to the goal node, it can be like a podcast or something. Displacement value, like the minimum value. I can't say it. I know what is heuristic. Short term of goal node, like.
Okay, short term for doing solution.
Short term or quick solutions.
Short or quick solution. Okay. Yeah, what is stochastic? Stochastic is random. I think there are different kinds of AI things that you can do, right? Strategies. It can be heuristic, it can be mathematical and statistical, it can be stochastic, it can be logical. You can do with logical. So yeah, A-star is a heuristic algorithm. Okay, what was your question?
Why not gradient dynamic keeps better?
Yeah, A-star is an advanced one. No, greedy and dynamic are the algorithm strategies. Okay, I think A-star is falling under dynamic thing, if I understand. Dynamic programming only. See, what are all the algorithm design strategies? Because that you are already asking detailed questions, right? Other than greedy and dynamic, what are all the other ones? Yeah, backtracking, branch and bound. Then brute force. Brute force is a straightforward approach. Brute force, greedy programming, dynamic programming, backtracking, branch and bound. Okay, I think that's it, right? Anything else? Yeah, divide and conquer. Yeah, very good. That is one very good technique, right? So these algorithm design strategies, right? You please try to understand the time complexities, space complexities, because if you want to go into any dream company, so more of data structures and design and analysis of algorithm questions will be asked. How do you want to store? What data structure is suitable for certain operations, and so on? What do you think you should have? So all the searching, sorting, time complexities, all these are very important. Okay. So here there is one more topic called as deep Boltzmann machines. Okay, there are two headings are there. Deep belief network is there, deep Boltzmann machines are there. They are mathematically very complicated. So I have removed all the complexities and I am giving you only one slide to understand the difference between a deep belief network versus a deep Boltzmann machine. The difference is that in a deep belief network, right, they are directional. But in a deep Boltzmann machine, they are all unidirectional. Sorry, bidirectional. That is the only difference. Actually, deep Boltzmann machines are very complicated. Deep belief networks are little better than deep Boltzmann machines. This can be used in real world use cases. These are more complicated because you have that directionality also here. These deep belief networks, like I showed earlier, right? Movie recommendation and all, right? You can use. There is a direction here, though I have not shown here. There is a direction. So deep belief networks have a direction. Deep Boltzmann networks don't have a direction. You have to keep that in your mind. See, why we are dealing with Markov chains, Markovian decision processes, Boltzmann machines, and Boltzmann deep belief network. These are mainly used for recommendations, association rule mining, and there are wide variety of applications across different domains. In electrical engineering for signal processing and all, right? If you treat everything as a signal, it is used. That is the reason why you guys are studying. Now with here, I am, one particular topic is over. The next topic is, the next topic will be transformers. Okay. So before I proceed with the next topic, right? You know what we have learned? Just at least the names of what we learned, right? Markovian chain, Markovian decision processes, Boltzmann machines, Bellman algorithm, restricted Boltzmann machine, deep belief network, deep Boltzmann machines. These are all the topics that we covered till now. Okay. Now I go to the next topic, which is nothing but transformers. transformers. So here this is very important in this particular now current scenario, because see what is Gen A, ChatGPT and all. What is the basic architecture of a ChatGPT? It's a transformer, right? What is GPT? Please expand GPT. Generative. I think I get your answers from here and here also, so I'm asking here. Okay. What is GPT? GPT, I want expansion for GPT. Pre-processing, pre-trained, yeah, generative pre-trained transformer. Why I'm saying is that transformer is the basic architecture in GPT. Okay, transformer is the basic architecture in GPT. So you need to understand what are the components of a transformer, which I am going through in detail in the next 40 minutes or 45 minutes. Okay. See, in the interview when they are asking you, you're learning so many subjects. They will say, guys, you use ChatGPT, you will say yes. If you are not even able to expand GPT, what is the use? Generative pre-trained transformer. Okay. So the basic architecture of GPT is what? Transformers. What are the different kinds of transformers that are there? Bird and distilled bird, basically. Okay. So we will see what is the architecture of a transformer. Before I go to transformers, we need to understand something like a natural language processing. NLP we need to understand. Okay. NLP means what? The way how you are processing your text and unstructured data, right? Sentences, text, paragraphs and all is called as natural language processing or natural language understanding or natural language translation. Your Google Translate is translating text from one language to another language. How are you processing your text? You have a video, right? Okay, you are getting a transcription there. Somebody is talking, he is able to give you the subtitles. Automatically speech to text translation is happening. So all of these things are happening with the help of NLP, natural language processing. So I don't know if you have already studied NLP. Have you studied? No, not yet. Okay. Okay. So there is an input text. Okay. So let the input text be. This is the input text. Okay. The basic concept what happens is that text means what? There are two types of data: unstructured data, structured data. Structured data means like how you are seeing for a movie recommendation, right? User, rows and columns. Unstructured data means the data is there in the form of text documents, PDF documents, Word documents, lot of text. How is the text? It's the form of sentences. Sentences, paragraphs, it's called as a corpus of text. Okay, if you look here, there is like, suppose you are having a line called as, this is the input text. The basic thing that happens in NLP is, you will have to do tokenization. You will have to do something called as a tokenization. That means that each and every word in this particular text is a token. This is a input. Even the dot also is a token there. Okay, this is called tokenization. Even this is like CLS also is a token. SCP is a separator token. CLS is called as a classification token. Okay, every token internally for machine learning algorithms to work, you should give a number. It will not take it cannot process any string data. It has always to be in numbers if you have to process anything. So everything will be given a number. Okay, so every word there will be given a number. So this is called as a classification token. It has got a token ID. Token ID is this one. There is a separator. Separator also has a token ID. So every word there will have a token. Token ID will be there. Okay. After tokenization is something called as embeddings. There are word embeddings. So what will happen is that your particular token, say for example 101, is now represented as a 3-dimensional embedding. That means what? A 3D vector. 3 values are there. It's a 3D vector. This is also given as a 3D vector. But usually you will have 768. I mean, for a bird and all, you'll have 768 dimensions. Not 3 dimensions, 768 dimensions. Means what? You'll have a one length, one column vector which is having one column but 768 rows in that. Here it is 3 dimension. Why is it 3 dimension? One column, 3 values. Okay, so it's a one, I can say 3 into 1. If I give the matrix, right, this is like a matrix, 3 rows and 1 column. But in a bird, you will have 768 into 1. Means 768 dimensions you are having. See, I can visualize 3 dimension how it will look. Can you visualize 768 dimensions? That is the complexity with which a bird model is coming. Okay, so what are these embeddings? You may ask me, ma'am. I don't know what is an embedding. What is an embedding? So what they did is like they analyzed the vocabulary of English and they formed a set of tokens that can repeat over a period of time, and they have given a specific kind of a dimension for each and every token. Okay, and the beauty of that word embeddings is that the semantics also is being captured in that. You will be able to know if there is king, one word called king, another word is queen. Whenever I am giving an embedding, right, you will understand how king and queen are related. You will be able to understand the meaning of it. Suppose there is something called apple. Okay. Apple will also be given a token ID. But apple can mean different things when it is placed in a distance. Apple can be a fruit, apple can be a company, or apple can be anything else also. Okay. So depending, that is where attention is coming into picture. But as such, every word in English, what they have done is they have identified all the different vocabulary that can form in English, and they have given different token IDs, and every token ID is represented by a n-dimensional vector, which is called as a word embedding. This is very, very important concept whenever you are doing NLP processing. This is a boom in the industry. NLP processing is a boom. If you are NLP engineers, you have this many number of jobs are there. Okay, so this particular example that I am telling you here is how it is happening internally. Any questions still here? We will take a break at 12 o'clock, is okay?
12:30.
12:30. Okay, we take break at
1:30 to 1:50.
Okay, no problem. We will listen to your friend. Okay. We can take break at 12:30. Okay.
I will ask.
Yeah, please. So here, there is one sentence. Let us look some time, take some time to understand what is happening here. Okay, there is something called as a statement. Input sentence is called as I love dogs. There is a sentence which is called as I love dogs. Okay, so how the tokenization and pre-processing is happening in a distill bird. Okay, in bird and distill bird, the vocabulary is around 30,000 words and all. The dimensions are 768. Okay, so initially when you have I love dogs, full stop, what are all the tokens that are there? I is one of the token, love is one token, dogs is one token. One more thing, in NLP you are having something called as a stop words. Stop words means words that are coming and that are coming, I am, the, okay, a, and the, all of these will come under stop words. Okay, which means that they will occur quite frequently and we need not be bothering much about that. But other than that, other words are there. Okay, so in NLP what they will do is first they will remove the stop words and they will try to form a vocabulary of unique words. And then they go with the other ones like tokenization, embedding and so on. So initially now here forget about stop words. Now we are having a sentence called I love dogs and with a full stop. So there are 4 tokens. Like I told you, each and every small thing, comma, full stop also is a token. So what will happen? First tokenization, each and everything is separated. Adding special tokens. So what we are doing is for every sentence, before the sentence we are putting CLS token. At the end of the sentence we are putting separator token. CLS means classification. It is telling the model that the text that is coming next, you please, the text that is coming next, you please try to pay attention and classify the text. Okay, so there are two more tokens that got added here. So CLS I love dogs dot separate. So how many tokens are there altogether here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 tokens are there. So every token will have a token ID here. So CLS is having 101. Separate is these are constant. The IDs are constant. 102. I is having 1045. Love is having 2293. Dogs is having 3899. Okay. So these are all the steps that are happening when you are calling that function distill bird with some input text, right? Now next, after token IDs are there, what is the process that you are doing? Padding. What is padding? Okay, because there are so many sentences that can be there. Meena is going to shopping, so I would love to see a movie as well as eat outside. So the sentences can be as long and as short as possible. But what we will do is, based on the entire set of sentences, we will try to come up with fixed length. We want to maintain a fixed length depending on the largest sentence that is there in the vocabulary or the repository. So based on the corpus repository, they will fix a fixed length for the statements. So here the fixed length is given as 20. Okay, so we have only 6 tokens that are available. For the remaining all, we will do a padding with 0. So we have taken that every sentence will have a fixed length of 20. Why do you want to take a fixed length? Whenever you are taking fixed length of the sentence size, right, it will be easier for the machine to process. Otherwise, it will be difficult for it to process vectors. These are all, at the end of the day, they are all vectors. Okay, these processing vectors. When it has to process multiple length vectors, it will be difficult. So you want to make uniformity or uniformity across all the sentences. You will, now it is fixed as 20. It can be 30, 10, depending on your corpus. You can fix the length of the sentence. Here it is 20. So apart from all of these tokens, remaining zeros are all added. Okay. So next, what is happening? Creating attention masks. Very, very important. What are attention masks here? Attention masks means we are telling that in their entire set of tokens, what are the actual tokens and what are not the tokens. If it is an actual token, we are giving 1. If it is not an actual token, we are giving 0. All the actual tokens are given 1 and whatever is not an actual token will be given 0. Okay, so we are telling the system that, okay, pay attention whenever there is a 1, that is a token, take it as token. Whenever there is a 0, then means it is not a token. At the end, what you are having, generating token type IDs. Here what you are trying to do is, here we are having only one sentence. If you are having more than one sentence, 1, 2, 3, 4, 5, then this will come into picture. We can actually differentiate between one sentence to another question using the last one. So these are all the parameters that you pass when you call your distill bird or bird. All of these things you need to tell. What are all the steps that are there? Tokenization, adding special tokens or nothing but token IDs. Okay, sorry, adding special tokens, which is nothing but CLS and separators. Yeah, adding token IDs. Padding is nothing but making a fixed length statements. Then you are doing attention masks. This last one is coming into picture when you have more than one sentence, which I will show you. Okay, now you have another sentence also. I love dogs, dogs are great. Now you see here. So, I love dogs, full stop, dogs are great, full stop. So, overall you are having 1, 2, 3, 4, 5, 6, 7, 8. 8 tokens are there. So, when you add special tokens, it will become, CLS is there. After one sentence is completed, you will have a separator. Okay, not at the end. After every sentence completion, you will have a separator and then you will have a separator towards the end. Therefore, 8 plus 3, 11. Altogether, you are having 11 tokens. Okay. All these 11 tokens will have the token IDs. If you see here, everywhere separator is having 102 value only. 102, 102. CLS everywhere it is 101 only. Other things are all there. Token IDs are all there. Okay. Now when you are doing padding, here also I am assuming that you are having a fixed length padding where you are putting that additional after 11, 9 more digits are there. That 9 digits you will put with 0. Now when you are creating the attention mask, you are telling that, okay, whichever is token will be 1, whichever is not token will be 0. Here at the end, now you see the difference. Because there are 2 sentences, right? Just to differentiate like a binary. Okay, wherever zeros are there, that is the first sentence. Like a CLS, I love dogs. Separate, I love dogs, full stop, separator. This is all one sentence. Next one. Dogs are great, right? That is all with one. In order to differentiate between the sentences, you will be giving a set of 0, 0, 1, 0, and so on. So the last one is used to identify the different set of sentences. Okay, so this is what is the basic process happening. If you are able to understand this, right? It's like I am giving you in depth what are exactly the verbs that are there in NLP. Why I am explaining all this is my aim is to make you understand what is a transformer and what is the internal architecture of a transformer. Transformer is the heart or the building block of a GPT, generative pre-trained transformer. Okay, that you are using now currently, right? Okay, now this is the architecture of a transformer. Entire thing is an architecture of a transformer. This is for bird and this is for distilled bird. They both are transformers only. Bird and distilled bird, both are transformers. So what is the difference between both of them? Everything is same. Bird is this way, distilled bird is this way. Everything is same except the fact that in distilled bird you are having only 6 transformer layers. In bird you are having 12 transformer layers. Okay, so distilled bird is 40 times more efficient compared to bird. 40 times more efficient. Even in terms of consuming space also less. So distilled bird is more efficient. Only 10% it will occupy space compared to 10% only it will occupy, and 40% more efficient than normal one. The difference lies in the reduction of the number of transformer layers in distilled bird. You are having filters, that is called as distillation. You are having filters in order to reduce the transformer layers. These are all one after the other layers that are there. But basically what you need to understand is, in any transformer, initially you are having a tokenized text. Then you are having embedding layer in any transformer. Suppose anyone can ask you in the interview. So what is the basic architecture of a GPT? It is a transformer. What are the components of a transformer? You are having a tokenization layer, you are having an embedding layer, and you are having other transformer layers. Okay, each and everything is a transformer layer, and finally you are having a prediction layer and an output. But each and every transformer layer internally, how is it looking? It is looking like this. Okay, I am having a very detailed explanation in further slides also, but this is how it is looking, how a transformer is looking. Okay, so in a transformer you are having key value and query pairs are there. Everywhere you are having key value and query pairs. And multi-head detection. It is actually given with a plus symbol, it is getting added up to normalization and then a feed-forward network and so on. Then finally you are getting your output. So, if you have read a paper, okay, the main components of a transformer are what? Tokenized text, embedding layer, transforming layer. In the transformer layer, right, the main thing is what? Attention. You need to understand attention. Okay, there is a paper called Attention is What It Needs. It's a very famous popular paper, research paper. The name of the paper is Attention is What It Needs. We need to understand. All the we are able to generate, transformers are used for generating content, right? We are able to generate content only because of that particular characteristic called as attention. Attention is what all it needs in a transformer. You need to understand what is that. So, yeah, when are we taking a break?
12:30.
12:30, okay. Yeah, so now we'll go to the next one. See, this is what I am telling you. This is nothing but how you are representing in a 3-dimensional. This is an example where you are having a 3-dimensional diagram. It is not about word embeddings, I am just representing you. If you are having something like a wings, engine and sky, there are 3 dimensions are there. There are some points are there. Okay, so helicopter, 0. Okay, x-axis is 0, y is 2, okay, and z is 4, 0, 2, 4. Okay, 0, 2, 4. Drone is there. Where is drone here? 0. There is x-axis value is 0. Y-axis is 3 and z-axis is 3. Why I gave you this example is so that you can visualize any 3D diagram. Similarly, you will have, these are only 3 dimensions, right? Similarly, this particular vectors, everything is a vector. Why is it a vector? Somewhere in the space you are having. So any point that is there in the space which is having x, y and z coordinate is called as a vector, right? This is just a visual representation of how a vector will look like. So similarly, you are having the word embeddings also. Word embeddings also are 768 vectors, one-dimensional vectors. It is having 768 one-dimensional vectors. Okay, so a transformer is internally like this. It is having input. It is having an input embedding. There is a positional embedding that is there, and then there is an attention mechanism that is there. Then you are normalizing and giving it to a feed-forward network, and then you are having another normalization. So, okay, what is the difference between a RNN and a transformer? From this diagram, can you guess?
RNN encodes everything separately, separate word. And
Here also separate only, na? Here also separate.
it takes completely, it accesses complete, it encodes complete.
No, main difference is that RNN, right? It is mainly used for time series. I mean, the cat is black. It will go one after the other. At time t, this goes t plus 1, t plus 2, t plus 3. So it goes one after the other. Input goes one after the other. But in a transformer, the input all received at once only. That is, this is like sequential. Because you see, sequential, one after the other. But here it is all at once. That is the main difference actually. Okay, so this transformer is actually more powerful than an RNN. That's what I just wanted to let you know. That is the internal working of an GPT. Okay. So now, okay, I wanted to explain more of this one. Okay. I wanted to make you understand what is the positional vector, what is happening in terms of attention. They are all matrix operations only. You should be able to, enjoy or show gratefulness to maths. Because of maths only we are able to generate new content. Okay, so that's why I wanted to take a moment to actually give you the mathematics behind working of a transformer. So what is happening is, in transformers there is something called as positional encoding. Okay, you already know that there is input is there. Input you are tokenizing. After tokenizing you are having an embedding layer. After embedding layer you are having a n-dimensional vector. Now these are the token embeddings. Suppose you are having I am a robot. I is having an embedding, am is having an embedding, A is having an embedding, and robot is having an embedding. Because that in a transformer all are fed at once, you should understand the position in which that particular word is placed also. So the position is given by a positional vector, which is nothing but P0, P1, P2, P3. Okay, so the overall embedding will be a sum of the positional vector plus the embedding. E1 plus P0, AM plus P1, A plus P2, E robot plus P3. Okay, suppose if the token embeddings are given like these things, right? This is only a 3D, but usually you will have 768. If the token embeddings are given like E1, EAM, EA and E0, right? So, if the embeddings are there, how are you calculating the positional encodings of those? Okay, the positional encodings are calculated based on whether the position is an even or an odd position. If it is an even position, you have this formula. And if you have an odd position, you have this formula. Okay, so I don't know how many of you are listening, but if you see here the positional encoding formulas, right? They are having sine and cos functions. Okay, see the beauty of maths. They are having sine and cos functions in order to give you the pattern for the positional encoding of the vectors. Okay, why sine and cos are used? What are the two main reasons why sine and cos are used? Because sine and cos are continuous functions and they repeat themselves over one frequency. Sine 0 will repeat like every 360. Sine 360 is the same 0. Cos is like same thing. Okay, so sine and cosine also they are used for continuous because they are continuous and they are differentiable, and then because that they have a repeated pattern. The combination of sine and cosine can be used to represent the position of the vectors. Okay, this is the formula that they are giving. The positioning encoding, P is nothing but the positioning encoding. This is the position 2i is equal to sine of cos by 100 to the power of 2i by d. Okay, I is nothing but the position and d is nothing but the number of dimensions. Okay, so here, yeah, the reason why sine and cos are used is because of the pattern. Okay, sine and cos are continuous functions. and they are repeating for regular intervals. Okay, so here using the formula, we are calculating the, so this is I am a Robert, this is the token ID, and these are the positional encoding, the formulas. Okay, this is the 0, this is the first index, 0, 1, 2, 3. So depending on the formula, they are calculating the values here. Okay, if it is an even, these are even, 0 and 2 are even, that's why you are getting sine. Odd ones are cos, 1 and 3 are cos. So you are applying the formula and then you are calculating the values. Okay, now this is what is happening internally. Okay, so you have an input vector, you are doing an embedding, and there is something called as a query, key and value. You will have to calculate all these values. How are you doing that? Okay, there is a linear transformation. This is nothing but an artificial neural network. That means you are multiplying the embedding vector with this one. Nothing big, it's just a mathematical multiplication. And then you are getting a query matrix, key matrix and a value matrix. The query matrix, key matrix and value matrix are also in the same dimensions as that of your word embeddings. Okay, you have an embedding, you have a positional vector, and then you have a query, key and value. Okay, all of these together, I have the very important thing. This is the attention. Attention is what it needs. This is the attention that they are talking about. Okay, the query, key and values. The query, key and values are here. So what you are doing, whenever you are having an input matrix, right? Whenever you are having an input V1, V2, Vn, that is given to the query, key and values. These are linear transformations or ANNs that are there. Okay, what you are basically doing is a dot matrix multiplication. You are multiplying this key with the key and query. You are doing a matrix multiplication. Okay, and then you are also doing like once. Why all of this we are doing? I'll tell you. So all of this, right? This is called self-attention. This entire block diagram is called as self-attention. Very, very important. Okay, so this is where, so what are the operations that are happening? Nothing but they are all vectors and they are basically doing matrix, dot matrix multiplication and addition only. Okay, here you are multiplying these two, that you are trying to normalize. What is normalization? Bringing the values between 0 and 1. You are normalizing and then you are doing again matrix multiplication of that one with values and then you are getting your output. So the V values are getting ultimately transformed to Y. The entire part is called as a self-attention. If you are having all of these self-attentions one after the other, it is called as multi-headed attention. Okay, if you see here, right? This is the multi-head attention. One single self-attention placed one after the other is called as a multi-head attention because you have to do it for each and every word you have to do. I am a Robert. For I, every token you need to do. For first token, second token, third token, fourth token. So and so on you will be doing. It's called as a, all this attention, self-attentions are placed one after the other. It's called a multi-headed attention. And so these are basically the dot matrix, dot product of matrices. Okay, so if you see an example here, right? Step-by-step calculation of attention mechanism. Okay, so first sentence is there, sentence is being added, special tokens and tokenized. Then you have the, for every token you are having an embedding layer. We are assuming that we are taking here only 3 dimensions, but usually it will be 768 dimensions. Okay, for each and every word we will be taking. Okay, this W, Q, K, V are nothing but your key, value, query. Key, value, query, W, they are nothing but vectors or weights. Key, value and query, I'll show you here. The key, value and query. The key, value and query are W. The key, value and query are these W matrices. So you are going to calculate the W. In general, you will have this kind of a weights. But because we want to make it simpler, we are taking only 3 dimensions. Assume that the WQ, query, key and weight matrices are already given, right? 3 by 3 matrices. What we are actually trying to do is like, you will be multiplying your key vector with your input. Okay, it is nothing but a dot products multiplication. You know, right? x1 w11 into x2 w21 into x3 w31. Okay, all of that will be. So it's a 1 row 3 column 3 by 3. which is nothing but 3, 3 cancel 1 by 3. You are getting K1, K2, K3. K is nothing but your key vector. Then the vector matrix size and your embedding size will be same. Here we are assuming that we are having embedding only 3 dimensions, but in general you will have 768 embeddings. This is how you are arriving at your key vector and query matrix, one after the other. For each and every token you will calculate that. Dot product of that, right? So you will be at the end of that you will get the key matrix for each and every input. Word. I am a robot. For each and everything you will get your key matrix, value matrix and query matrix will be there. Okay. So what is the use of query matrix? Why are we doing all of this key, query? Why are we doing dot product and all? At the end of all of this, what is that I am going to get? Okay. So I'll tell you one thing. What is the statement there? What is the statement that you are passing here? You see, the bank of the river was flooded. Okay. So the system is to understand this. Okay, if you take the words individually, if there is no attention mechanism, if you are not doing whatever I am telling you now, right, what is going to happen is that it will not be able to identify whether the bank that they are referring here is a normal bank or is it a bank that is near the river. Okay, because of the words river and flooded only, I am able to understand that bank is coming in a context with river and flooded. Okay, otherwise it can be normal bank also, right? Any financial institution bank. So that attention mechanism, see the beauty of math, because of that mathematical operation. And at the end I am going to get one particular vector. If at all the value of that particular vector is high, if the value is high, which means that we have to pay attention to those words and then identify how bank is related to that. Okay, that is the reason why we are doing all of this maths. Because attention is what it is all. Otherwise, any other network would have worked. But we need to understand the semantics here. That's why attention is having a lot of significance there. So, at the end of all these operations, right? Yeah, this is one main example for word embeddings. This is in a 3-dimensional space. All the points are scattered. Okay, you are having around 300 dimensions. Assume that you are having around 300 dimensions. What do you understand from this? This is an example of a word embedding. Okay, in word embedding, whenever I say something like a query means the string that we are giving, kitten. Okay, it is related to cat. Okay, that's why you are having this small bubble. It's also related to dog. It's also related to wolf. It also somewhere related to chicken. Okay, if you are having apple, banana, they are all in the dimension space in one place. Apple, Google, they are all in one place. Okay, so what is this representing? That is like whenever you are using any embedding, the vector values that are placed in the space, right, they are grouped together in one category. Okay, so you need to understand how mathematically they have built the word embeddings. We are not building. That is already given by researchers from Google, right? What was the first word embedding that we got? Clove. Right? So those word embeddings are like nothing but they are giving for every word they are giving a vector. What are those vectors? They are semantic representation, not just one number. I can also tell one number, right? No. They have written in such a way that words with similar meaning are falling in one group as a cluster. Words with one similar meaning are all forming one cluster. That is how they are giving the word representations. This is called as a vector database. This is one of the vector database. Whenever you write a query, it will check whether that particular query, the word that they are using the query, is matching to which particular thing, is what is checked here. Okay, so compute the query vector for the river. So like I told you, right, it's always a dot matrix multiplication between the embedding and that particular thing. So you are getting the key matrix here. Okay, why I am showing you this is, I will tell you at the end. So the below is the raw attention scores for the word river. Okay, for each and every token we are calculating. For CLS token, what is that? For B, for bank, for off, for everything we are getting finally one number. Based on the entire formula, we are arriving at one number for each and every token. So what are all the things we were using? We were using embedding, we are using a positional encoding, and based on that we are calculating key value and query pairs. And based on that we are doing a dot matrix multiplication, and then based on that when you are adding the final results you are getting this particular value. Okay, now what is this signifying? So at the end I am getting these values. CLS, the bank of the river was flooded and all that. Okay, now what you need to understand is that whichever is having like a bank is having 0.2. This is also 0.2. It means what? The bank and river. The system will understand that the bank is corresponding to the river. Other things are all very small, you see. They are having very...
And the dimensions are actually but we can feel
Now, just 3 minutes, I will wind up and then. Yeah, just 3 minutes. So, so here what we have to understand is that, see, if you look at all the values here, right? At the end of all of this, what you are doing a mathematical operation and you got the result here. For every token, you got a result. Now the system will actually, how it will understand? Bank is having 0.204, river is having 0.216. So these two are the values which are high in number. High in number, others are all very low. Negative, 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 negative. Only the ones which are high in number are these two, 3 and 6. So they are related. So you will understand that, and even flooded also, right? 0.096. So bank, river and flooded are all forming one group. So you will identify bank as something that is related to river and flooded rather than to a financial corporation. That is what I wanted to tell you. Okay, there is I need to tell about computer vision, fundamentals of computer vision, applications of computer vision, and some case studies are there. We will look after the break. So have a good lunch and then we'll meet whenever. When do we meet?
1:15.
Okay, 1:15 you can be there. Thank you. Thank you.